Many experimental tests have been performed within PERPETUATE project. A first set of tests were performed on the shaking table. The dynamical behavior of full-scale and scaled architectonic assets, an obelisk, an arched pier system, a masonry cross vault, and multi-drum columns under seismic action has been studied, taking into account both load-bearing and displacement capacity. The aims were to measure their limited displacement capacity under dynamic conditions and study the effect of different inputs. Moreover, a base isolation system for statues and artistic assets has been tested to assess its effectiveness. In the second set of tests, the shear behavior of ancient-like stone masonry walls has been studied. Also in this case, both load-bearing and lateral displacement capacity were analyzed. Besides defining the mechanical properties and drift values corresponding to limit states, these tests aimed at understanding the relationship between the mechanical behavior of masonry and covering artistic surfaces. The third set of tests, carried out in situ, were oriented to assess the effectiveness of some strengthening techniques on masonry walls.
The aim of the shaking table test in PERPETUATE was to define the proper limit state for cultural heritage assets and to correlate those limit states to the seismic ENEA. It was obtained by the direct measurement of the displacement at several points of the structures and to correlate those displacements to the damage states. The structure under test was reduced scale model of the Egyptian obelisk in Piazza San Giovanni Laterano in Rome, a full-scale model of the vault of the Mosque of Algeria in Algeria, and a reduced scale model of a Roman arch. The direct displacement was measured by using several markers positioned at the nodal point of the structures and measuring the relative displacement of those markers to a reference points. It was also possible to, in this way, to validate the numerical models, because the markers were positioned at the nodal point of the finite element model of the structures. It was also possible, by using this possibility to measure the displacements, to share the experiment in remote mode and to allow the partner of the project to participate in the experiment in within via internet, and also to exchange the data during the experiment. So possible also to direct dialogate our partners and to participate in the experiment.
A scaled model of Lateranense obelisk has been tested at ENEA Caserta laboratory in Rome after a detailed in situ campaign of survey and ambient vibration tests. The obelisk is made by 3 blocks, connected only by pin joints which allow rotation but prevent from slidings. The theoretical capacity curve obtained by the macro-block model has been validated by pull and release tests, which also give the elastic period of the obelisk and the damping due to impacts and viscose dissipation. The obelisk mainly moves as a rigid body without significant rotations in the upper joints. Shaking table tests have been performed by using a properly defined input time history, which has been scaled in order to perform experimentally an incremental dynamic analysis. The experimental results are in good agreement with the displacement demands obtained by the PERPETUATE procedure. Interesting effects due to the geometric irregularity of the base section have been observed. The tests on the arch-pier system have been carried out on 1:10 scale model. They have been oriented to assess the increasing in the load-bearing and displacement capacity provided by the introduction of tie rods of different stiffness. The mock-up is made of 43 rigid plastic blocks. In a first phase, the model has been tested at the University of Genoa laboratory under static conditions by adopting the inclined plane test. These tests allowed us to define the static collapse multiplier and typical collapse modes and to provide preliminary results for the following dynamic tests. Shaking table tests have been performed in a second phase at the ENEA laboratory in Rome, with the aim to analyze the dynamic behavior of the system. Incremental dynamic analysis with 2 different scale inputs have been carried out in order to define the peak ground acceleration and limit displacement at arch collapse. Tie rods have increased meaningfully the load-bearing capacity of the system. The increasing of displacement capacity provided by more deformable tie rods has been also demonstrated. Finally, the tests have been very useful to validate the theoretical models proposed within PERPETUATE procedure. A very detailed full-scale model of a cross-vault of the D Mosque in Algiers has been tested. The aim was to evaluate the stiffness and displacement capacity of vaults under seismic actions, when the shear displacements are imposed at their springs due to the global behavior of all building. Random and ambient vibration tests have been performed in order to estimate the fundamental frequencies and modal shapes. The dynamic response has appeared to be in good agreement with the results of a finite element model. Shaking table tests have considered a time history recorded in the Bombardiers earthquake 2003 and deconvoluted to the site of the Palace of the D in Algiers. This time history has been applied many times, gradually increasing the peak ground acceleration till to collapse. The vault collapsed for 0.4 g, a value which is quite high for Algiers. A typical collapse mechanism was observed, with the formation of hinges in the vault and detachment from the side walls. ENEA has also proposed an innovative marble seismic basement for artworks and statues in order to isolate them from seismic actions. Shaking table tests showed their effectiveness in the case of bronzes of Riace. At the University of Athens, the rocking response of classical columns to strong seismic motion has been investigated through shaking table tests.
I'm Cenacolo of the National Technical University of Athens, and we are now at the Acropolis of Athens. There are many such monuments all over Greece, but this is known as the Acropolis, simply because it's the most important one. The scope of a PERPETUATE project is to safeguard such monuments against a seismic risk. To do this, we have to understand their vulnerability. The problem with structures such as this one is that they are composed of multiple columns, as you can see, and each column is composed of multiple pieces, the so-called drums. Each piece is not connected by any means to each other, so the only force that is keeping them together is actually the force of gravity. So one might say that the ancient Greeks perhaps did not really figure it out correctly, but since it has been sitting there for more than 25 centuries, maybe there is more into it. So we should get back to the lab and see what we can do about it.
In particular, a series of experiments on the shaking table of the Soil Mechanics Laboratory of National Technical University of Athens has been conducted to investigate the dynamic response of single or two connected multi-drum columns, namely a portal. A database of results from a total of 125 tests was developed as the specimen was excited by a large set of idealized pulses, as well as real records from various earthquakes around the world. Results have provided valuable insight of the different aspects of the response taking place for different characteristics of the base excitation. The major conclusion of this experimental campaign is that typical multi-drum classical currents can survive the ground shaking from strong ground motions.
And this is the actual model we used in the shaking table tests. As you can see, it is composed of two multi-drum columns at a scale of 1 by 5, and on top there is an epistyle. What we actually did is that we took pieces of marble from the very same place the ancient Greeks did, construct this model. The model was subjected to a variety of seismic shaking scenarios using seismic records, real seismic records, from Greece and also abroad. In each case, we measured displacements, rotations and accelerations of each drum, and it was proven that exactly because the drums are not connected to each other, they can rotate and slide, and this leads to tremendous dissipation of energy. Actually, based on the results of the shaking table tests, it may be concluded that such monuments can easily last for 20 more centuries.
In this video clip, the response of a single multi-drum column excited by the strong one-cycle Richter-type pulse of an acceleration amplitude greater than 0.8 G is displayed. Notice that the column segments are not connected to each other. The specimen of a portal is now excited by the notorious GMA record from the disastrous earthquake at Kobe, Japan in 1995. The maximum base acceleration is almost 1G.
The most relevant contribution from the PERPETUATE project in respect to the as-built information for the masonry structures are basically large amount of information gathered from in-situ tests, carried both on brickwork and stonework masonry. Also, the tests carried here in laboratory provide us valuable information regarding the performance limits of the artistic values that are attached to the stone masonry. On the other hand, a comprehensive usage of non-destructive test methods enable us with the soft clustering data fusion method to get a clear picture of the texture behind the artistic values and to get the information about the morphology of the walls.
In the experimental campaign carried out at the University of Ljubljana laboratory, the behavior of multi-leaf stone masonry walls under shear and compression loads has been analyzed. In particular, the tests aimed at defining the maximum strength and displacement capacity of walls and at analyzing the mechanical behavior of applied plasters. 18 specimens made of limestone outer leaves, lime mortar with stone rubble inside with and without connection through leaves have been tested. The walls were finished with 2 layers of lime plaster. In the first phase, 4 compression tests have been carried out. Then, 15 cyclic shear tests with different level of precompression and different boundary conditions have been performed. Depending on these 2 variables, flexural, shear or mixed failure modes were obtained. The strength of the walls obtained is consistent with that proposed in the Italian guideline for the seismic protection of cultural heritage from seismic risk. The behavior of plaster has been analyzed with reference to different reference limit states. First detachments of the plaster, first crack of the plaster, significant but still repairable detachment, partly or entire collapse of the plaster. The drift of the walls has been associated with each limit state in order to correlate the structural behavior of the wall with the mechanical behavior of the plaster.
These are diagonal compression test campaigns made in The masonry simulates that of L'Aquila, which is a stone masonry with very weak mortar. On the first step, the lateral load is applied, and then it is taken fixed for all the tests. And then the diagonal load is applied up to collapse. We measure the displacements on the panels by means of this marker, which are analyzed by an infrared camera, able to tracing the displacement of each point in the test. The infrared camera is a very innovative system for catching the displacements, and it's very easy to use, and it's also easy because it makes us able to monitoring during the test a very large number of points on the camera. We choose these systems because besides the structural behavior of the panels, we want to monitor the behavior of the plaster applied on it. We want also to analyze the detachments of the plaster from the masonry walls. And to this aim, we have a thermal camera, which is able to analyze the place where the plaster attached and during the test. In particular, we make a thermography after the end of this cycle of the test, in order to analyze the evolution of the plaster detachment.
In fact, also in this case, the panels were covered with a plaster simulating ancient ones. In particular, the surface finishing was made of 3 layers of lime plaster with different thickness and aggregate gradient. Moreover, a pre-seismic damage was artificially introduced by inserting a wafer paper sheet between the first and the second layer of plaster. Very low values of peak strength have been obtained, mainly due to the type of masonry considered. However, despite the very regular masonry pattern considered, the image patterns were coherent with those expected. Mechanical results were analyzed with literature models, finding a good correlation.
Results of experimental tests are very important to gather real information about load-bearing element strength and deformation capacity. That is vital for realistic structural analysis, and on the basis of experimental results the safety factors can be lower, and so the less intrusive strengthening techniques could be used. Different tests that were not enough experimentally investigated before, like walls common in Islamic architecture, or effects of tying the arches, and also strengthening of masonry walls with FRPs, were tested during the PERPETUATE project. Experiments were crucial to get the response on lateral loads of those different structures, and also to gather the performance points that are needed when analyzing cultural heritage building by the PERPETUATE procedure to get the resistance on earthquake loading. Okay.
In this test campaign, different strengthening techniques have been analyzed. In particular, the employment of carbon or glass fibers reinforced polymers and stripes in different geometrical configurations have been considered. All the tests have been performed in situ on 2 buildings that were going to be demolished in few months. In the first building, sited in Slovenia, the reinforcement with diagonal or perpendicular carbon fibers reinforced polymers, large stripes have been considered. The results obtained show that the diagonal stripes increase the shear strength of the wall, but reduce its lateral displacement capacity. The perpendicular stripes further increase the strength, but provide also large displacement capacity. It has been then assessed that such setting of the stripes is preferable in terms of both strength and ductility. In the second building, sited in Slovenia, the reinforcement with glass fiber mesh and carbon fiber narrow horizontal stripes have been considered. The results obtained show that the glass fiber mesh meaningfully increased the shear strength of the wall, but slightly increased its lateral displacement capacity. The carbon fiber's narrow horizontal stripes increase both the strength and displacement capacity and is therefore preferable. The results are very clear by aggregating the shear strength and the maximum rotation capacity obtained. All the tested strengthening techniques provide an increase in the strength of wall, but the more remarkable differences are in the ductility. Perpendicular thick stripes resulted to be the more efficient.